So maybe the burning question in your heart is, well, Dr. Pierce, how do we decide if two reactants are going to go through an SN1 or an SN2 reaction? And that is a great question. There are 4 factors that we use to predict whether the reaction is going to go through an SN1 or an SN2 mechanism. And we're gonna go through those today. We've already covered a lot of those in previous screencasts, but one of them is the alkyl halide. Whether it is a methyl, primary, secondary, or tertiary is gonna be our biggest key in helping figure out if we're gonna go through an SN1 or an SN2 mechanism. The next is the nucleophile. Is it strong or weak? Is the leaving group good or poor? And then about the solvent, is it protic or aprotic? Let's talk about the alkyl halide first. This is the most important factor in predicting whether a mechanism is going to be SN1 or SN2. And just as a review from what we've covered previously is that when you have an SN1 reaction, right, it increases here, the rate increases as we go from methyl, primary, secondary, and tertiary. And then if we have an SN2 reaction this way, then these are going to go through an SN2 reaction the fastest. So when we are trying to make decisions, if something is tertiary, it is going to go through an SN1. That's it. If something is a methyl or primary, it's going to go through an SN2. That's it. Now, the secondary is where we have a few, I wouldn't say problems, but where we have to dig a little deeper, because a secondary can go through both SN1 and SN2. Now, nucleophiles are another thing that we consider. And strong nucleophiles which generally bear a negative charge right, that are present in high concentration favor SN2 reactions, okay? Weak nucleophiles, which generally don't have a charge, are things like water and alcohols, right? Favor SN1 reactions, right? And they do this by decreasing the rate of any competing SN2 reaction. So here is a secondary alkyl halide, and I want us to look at this, right? It can go through a reaction with a strong nucleophile or a weak nucleophile. And so if we look on the next slide, right, the strong nucleophile favors the SN2 mechanism, right? And we get an inversion of configuration, and this is our product. A weak nucleophile favors that SN1 mechanism, and the first step here is the halide leaves, and now this water can approach from above or below. Now, you only have to show one arrow here, but you do need to show both the products here, okay? So, another thing that we can see is the leaving group that affects the SN1 or the SN2 reaction. And basically, a better leaving group increases the rate of both SN1 and SN2. So this doesn't really help us sort out the difference between an SN1 and an SN2. We just know we need to have a good leaving group if we're going to do either of these reactions. So we increase the rate of SN1 and SN2 reactions, right, as we get a better leaving group. but that's not really helpful for differentiating between the two. Now, solvents can also help us with this. Polar product solvents, and remember those are things like alcohols or water, they're going to have hydrogen bonding, generally favor SN1 reactions because of the ionic intermediates, are stabilized by solvation. So remember, we're forming that carbocation, and that can be stabilized through the solvation here. Polar A product solvents favor SN2 reactions because the nucleophiles are not well solvated and so are more nucleophilic. And this is things like acetone, DMSO, those type of polar A product solvents. So here is a summary table of the factors that determine whether it's going to be an SN1 or an SN2 mechanism. When we look at this, the most important factor is whether it's what type of alkyl halide it is. And so if it's primary or methyl, it's going to be an SN2. If it's tertiary, it's going to be an SN1. And then if it's secondary, it's going to be an SN1 or an SN2. And the mechanism here really depends on the conditions. A strong nucleophile favors the SN2 mechanism over the SN1 mechanism. So for example, deprotonated alcohol is a stronger nucleophile than a protonated alcohol. So that deprotonated alcohol favors the SN2 reaction and the protonated alcohol favors SN1. Product solvents favor an SN1 mechanism and aproduct solvents favor an SN2 mechanism. So my suggestion is to really keep this slide handy as you are working problems. So let's do an example. Okay, we're going to determine the mechanism of a nucleophilic substitution reaction and predict the products. And so we look here, and this already gives us the context clue. Look, it's going to be a nucleophilic substitution reaction, but it doesn't tell us what kind. And so this is a sneaky way to say, look, you have to determine whether this is an SN1 or an SN2. So the first thing you need to look at is the alkyl halide. When we look at the alkyl halide, we see that the halogen is attached to a carbon with only one R group. So that means that is a primary alkyl halide. So it must react by an SN2 mechanism. So now we're going to show that mechanism. When you show a mechanism, you need to rewrite the reactants. You don't have to put the plus, but you absolutely can. And we want to show that these electrons are coming here to attack that partially positive carbon. Because remember, this is very electronegative. It's going to withdraw electron density. This is very positive. Then these electrons are going to go on the bromine. So when we predict this product, we're going to use those arrows to help show us where we're forming new bonds. So I look here and I say, okay, nothing's changed here, nothing's changed here. Now at this stage, when I look over here, I see there's that red arrow, and that's going to be a new bond to that carbon. And then there's 1, 2, 3. So here's how I double check. I always go back and I count my carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. I have put in an extra bond. That's very easy to do, and that's a very good way that you can come back and catch it. So I'm going to come here and I'm going to take that carbon out, and I'm going to say, okay, my triple bond actually needs to go here. And so now I have 1, 2, 3, 4, 5. I also need to show the bromine. So it's very easy for these carbons, when you're drawing these stick structures, for them to get out of hand. And so a really, like I mentioned, a really great double check is go back and count your carbons. Let's do another example. This one has stereochemistry. Yay! So let's look at this one. Right? So the first thing we look at is the alkyl halide. And we see that that alkyl halide is attached to a carbon with 2 R groups. And so we say, great, that is either going to be SN1 or SN2. Okay, so now we have to look at other conditions to help us figure out if it's going to be SN2 or SN1, because the alkyl halide can be either. So we need to go over and we need to look at the nucleophile. The nucleophile in this case is OCH3. There's a negative charge. And so that tells us, hey, look, with that negative charge, that's going to be SN2. Okay? Then we look at the solvent, which is DMSO. And we remember that DMSO is a polar aprotic solvent, and polar aprotic solvents favor SN2 reactions. So all of this points in the direction of an SN2. So I'm going to come down here and I'm going to redraw my reactant. And I said you didn't have to put the plus, so I want to show something here without the plus. Now, I want you to notice that OCH3 minus does not have electrons around it, but you need to add electrons here so that you can show electron movement. So when we come in here, we're going to say, okay, hey, look, this goes through a backside attack, so it's going to attack here on the opposite side of the leaving group, and that chlorine is going to be the leaving group. So when it does this, I'm going to start writing my CH3O, right? And then we're going to see where it interconverted here. So you have an inversion of configuration. So you can't forget the stereochemistry when solving these problems. Now, the very last thing that we're going to talk about in this chapter just briefly is organic synthesis. And organic synthesis is really just the systematic preparation of a compound from these readily available starting materials using one or many steps, right? And many times what we do is we think backwards when we're doing this. So we have a product in mind that we're trying to synthesize, and we need to think about what we are going to react to synthesize this product. Now, nucleophilic substitution reactions, particularly SN2, are introduced, are really used to introduce a wide variety of functional groups into the molecule depending on the nucleophile. So this is incredibly versatile. Organic synthesis, right, is used to produce so many useful compounds in industry like pharmaceuticals, pesticides, and polymers. Chemists also can use these SN2 reactions in the synthesis of natural products. So when we talk about natural products in organic chemistry, we are talking about something that is produced from organisms, but maybe only in a really small amount. A really good example of this is Taxol. It comes from the bark of a tree, and to get Taxol, you basically have to kill the tree. But Taxol is used in cancer treatments, and it's a very effective therapy for cancer treatments. So chemists then used organic synthesis and synthesized Taxol so that we could still use it in cancer therapies, and we don't have to kill trees to get very small amounts of it. Now, when we carry out a particular synthesis, right, we tend to think backwards, as I mentioned. So, for example, if I want to make this guy, this is 2-methylpropanol, I need to determine 2 compounds that I can use to make this molecule. And you need to ask yourself, what's the starting material, right? So what's going to be my alkyl halide? And then what is my nucleophile going to be? And so when we do this and we think backwards, right, for example, I would think, okay, hey, look, I want to attach that OH group there, right? So I need my alkyl halide, right, to go where I need that functional group to be. And so I put the alkyl halide where the functional group is, and I leave everything else the same. And then I ask myself, what nucleophile do I know that can come and substitute for this alkyl halide and form an alcohol? Well, that's an OH group, and so that can come in and do that. We're going to talk more about organic synthesis in other chapters, but I just wanted to kind of go ahead and let you start thinking about it at the end of Chapter 7 here. So this completes our journey into Chapter 7. If you have any questions, please feel free to stop by my office.